by Ben, and the review we volunteer to speak about comparison between surface coping and density metrics.
No?
Okay, floor is yours.
So this probably won't be the best journal club you've ever participated in, but we'll try. So the journal that I read and we'll be talking about today is Optimizing the Photovoltaic Properties of Quantum Tellurium Quantum Dot Porphyrin? Is that how you?
Porphyrin.
Porphyrin. There we go.
Well,
Nanocomposites.
correct me.
Theoreticals.
Porphyrin?
So
Why porphyrin is called porphyrin?
it's from the Greek and it means like 4 rings or something like that.
Really? Oh,
I thought that was okay. I
You
don't know.
Another story?
I have another story, but I can be very wrong.
Okay.
The monarchs, like kings in ancient times, they had a specific color of dresses to separate.
It's Greek for purple. I remember now.
Okay.
It's Greek for purple. So not
So
not 4
porphyrin means
rings.
green to purple?
Purple. It was dye to bring color to the fabric. Yes.
Okay. So this was done by a pair of people out of India. So there we go. So let's look at the author's motivations. So the authors talk about the ongoing development of dye-sensitized solar cells. And specifically they talk about organic, inorganic. So like quantum dot solar cells, and they mention cadmium chalcogenides, which is your group 16s, your sulfurs, your seleniums, your telluriums, and porphyrins as dyes and different variations of the porphyrins. And their main motivation is that they saw that there was limited research of photovoltaic performance for these sorts of quantum dots. And so, there we go. So let's have a look at what they studied. So specifically they studied tetraphenylporphyrin in thiol-capped quantum dots, these cadmium tellurium quantum dots. So the quantum dot is covered in thiols and the porphyrin is tetraphenyl, so it has 4 phenyl groups around
Do
it.
they give number of thiol groups? And also, do they have hydrogen, like it's neutral, it's thiol or thiolate?
They specifically said thiol,
And
so
I don't know, you can
those
see
are
that there are
hydrogens.
hydrogens. Okay, so it's
Those are
thiols, okay.
hydrogens.
So it's neutral, okay.
So, yeah, and so there are 3 different variables, I guess, that they investigated. So they looked at different sizes of these quantum dots, so specifically 17, 34, 65, and 98. However, I found it interesting that they never brought up the 34 size quantum dots. They never brought them up again. So they also tried para-substituting these 3 phenyl rings on the TPP with nothing, the CH3, NH2, COOH, and NO2.
Any ideas how these groups are different? What kind of really main
So
difference is coming due to this group?
So
I mean, not for the results, but for the motivation.
the motivation for these, thank you, actually, I needed to talk about this. These first 2, the CH3 and the NH2, are electron donating groups, and then the second 2, the COOH and the NO2, are electron withdrawing groups. And so, yeah, that's the right order. So And then one of them, like the CH3 and the COOH, are both weak, and the NH2 and the NO2 are both strong. And so that's why they chose those four. So, and then finally, they tried adding a zinc center to the TPP. There are two configurations of this that we're going to touch on. And then there are two factors that they talked about when it came to the photoelectric properties, yes. So they talked about efficient electron transfer and spatial separation of charge. I felt like they focused more on spatial separation of charge, but they did touch on efficient electron transfer. So let's take a look at some of the theory that they talked about. So the main one that they talked about was the Marcus theory, and they specifically used this semi-classical model of charge recombination. The rate of charge recombination is this big thing.
Oh, so they really talk about, this is for a recombination. Maybe you need to explain what you mean by recombination.
So,
which charges do recombine?
So in this case, we're talking about the electron-hole combination, and the electron is excited, and so it creates a whole electron pair. Then the recombination, if I'm not mistaken, is the electron moving back into the hole. And so that's what this is looking
But
at.
they probably expect that the index A and B then in this case would stay probably for the state A, let's say electron, and B for the whole state, right?
Yes.
But they'll probably also assume that your A is sitting, let's say, on a quantum dot, and B is more related or localized on a die, or backward, I don't know, right? So like, you really expect that your electron and hole states should be on the different parts of the system.
Well, that's something that I'll touch on later, because they did some DOS stuff, and which shows like which has the hole and which has the die. But so the main thing that they focused on was this V. Everything else they just kind of said wasn't as important, and just kind of mentioned that this V, the electronic coupling between the initial and final states, is dependent on the overlap of the wave functions for the HOMO and LUMO, and simply said that because that the HOMO and LUMO were on different parts of the molecule in most cases.
So like they expect, they should like,
well,
the most interesting situation when the HOMO and LUMO are at different parts.
Yes, and so therefore there's very little overlap, and so we can assume that this is going to,
Very small.
well, it would actually be very large.
If V
Now
is
that I
very
think
small,
about that, that's the,
just a second, if V is very small, then K is very small,
so-
right?
yes, okay. V is very small because there's no overlap, or very little overlap, and so K is going to be very small as well. So, and then they also, that's not what I wanted. So they also talked about photoelectric conversion efficiency, which is
But
what?
before you go, just to kind of get everyone to know that Ben is first he's an undergraduate student, second he just started doing any kind of research in general actually in mid of May, right? So it's his first month actually over. So that's why, of course, to go through all these details in a formula probably would be a little bit challenging, but I hope there are people in the audience who knows what is a Marcus theory, right? And maybe we can go to the discussion and kind of just discuss what these coefficients, lambda, delta, G, well, I guess T is just a temperature there, or what is T?
Yeah, T is the temperature, the H is the reduced Planck's constant, and the KB is the
Yeah,
Boltzmann
so
constant.
looks like the main kind of parameters would be lambda and delta G. Any kind of help for defining these parameters and what they exactly mean? Okay, how many people have heard about Marcus theory?
Charbot has 300 likes or hits on his YouTube about Marcus theory.
So it mainly depends on the reorganization energy,
What is the reorganization energy? Lambda or delta G in this case?
lambda.
And what do we call the reorganization energy? Maybe, are we out again from the blackboard, whiteboard?
London presentation has a Marcus theorem, two parabola if you put it.
Okay,
So I mean, the minimum energy of the potential, the difference between the two is going to be your delta G, and then your offset going a direction will be part of the reorganization energy because it's more than
which is
nuclear
lambda,
component.
right?
Would you like to draw it?
Oh, yeah. And again, these two parabolas, they stay for the electronic
I
states.
trust you to do that.
Ground state and
I trust you to
excited
draw.
Electronic
what I
states
said.
of the system, right? So initial and final, let's say in your case it will be ground and excited state. If you talk about
Just
recombination.
finger.
Say, say we have something like this. So this is an S0, and say this is S1. So you have some values corresponding to these two different potentials. And so you have a difference like this, that'll be some type of energy, and then you have this type of value, which will be like a lambda.
And again, those who maybe knows where to get these values,
Thank you.
they just ignore it, right? Because they say, oh, overall it's small, so we don't worry about it. But in general, actually, we cannot just ignore this exponential part, right? Even if we can calculate the electronic couplings, we still need probably to include this lambda delta G. Any ideas how can we calculate, how to get, what is the main approach in getting these parameters? Either theoretically or, well, probably you're a statistician, so probably theoretically is a main purpose.
Like just in terms of getting those values? Well, I mean,
Or
if-
what kind of calculations should we
well,
run to get them?
If you run electronic optimization, you'll get the
Yes,
minimum
yes.
points. And once you start running something with a promoted electron in the excited state, then you can get those other potentials. Or you can have different nuclear organizations, so two different, same system, just move the nuclei around, and then you can start to see how the energy differs.
So in other words, you need to
parts
really
are-
make these potentials. And each point at this potential corresponds to slightly different geometry, right? For the ground and for the excited state.
Yeah.
And you either do really calculations based on molecular dynamics, kind of to establish, and you expect that they move really just a little bit. It's not like a huge change from the ground state, right? I mean, from the minima, from the equilibrium, but just a little bit. So you probably can get the surface potential for the ground state, then you can do the same for the excited state, optimize the excited state, and then maybe distort it a little bit. Assuming parabolic behavior, you know the formula k square, right? So you can, like, having 3 points is, am I right? 3 points or 2 points? 2 points is
You can
enough.
do it too.
Because it's symmetric, right? 2 points is enough. The minima and somewhere nearby is enough to kind of create a parabola, if you assume again that it's parabolic behavior. And then you can get this lambda and delta G just from your calculations. But this is even this type of calculations are actually not as simple to run in such big systems as they consider, right? So it would be really challenging to do this kind of dynamics and getting these potentials, especially for the excited state. For ground state, I think it's maybe not a big deal, but for the excited state, to optimize the excited state, this is where it's the most time-consuming and the most problematic one, and you already start doing the optimization of excited state for the ruthenium complex, or iridium, whatever you're looking.
Yeah.
So you run this type of jobs already for your research, and it's not done yet, right?
Few of them is done, right?
But you already probably notice it's much longer than what it was before, right? So it takes more time, and then we might be really surprised with the data because it will be not correlate with experiment. Usually we are pretty off with that. There is a way how you can calculate this and really put all these parameters to this model, right? But there's no guarantees that this calculation will give you really very good results until you really have the way to compare this with experiment. And plus, it's very time-consuming, pretty expensive, computationally expensive calculation. So yeah. So simple formula, but not as simple to get these calculations done.
Okay. So the second part of this slide is the photoelectric conversion efficiency. which they took from Gretzel's paper, actually. One of his 2009 papers, he defined this. And so this JSC is the short circuit current density, which is basically the current. And then this VOC is the open circuit photovoltage, or voltage of the system. This fill factor, they didn't really touch on, but my understanding is that it's the ratio of like the maximum power versus like the actual power.
What is your opinion about Ohm's law?
Ohm's law. Ohm's law is pretty good.
But do you remember the formula for the law?
I'm trying to remember how exactly it's organized. It's
There should be R, I, and V.
yes.
Some combination between the three letters.
So it's
You are the only participant in the conference.
voltage times current equals resistance.
What's the units for the resistance?
V equals I.
V equal
Yeah,
V equals
so it-
IR.
yeah.
Okay.
Yep. So
That makes
if you look at a plot of short circuit current density versus like your open circuit voltage, it would be something like
Maybe just draw it on a
Oh.
screen because so everyone can see.
have a plot like this. You would have some value going like this. Your fill factors at say your maximum values.
You should
Put the
probably
values
label
on your
those.
Y and X.
I
I mean, not the
which-
values, the
yeah.
physical meaning.
Well, okay.
Escape.
We'll just do V and J this way,
Okay. Or I.
or I. But yeah, so doing it this way, and the fill
V
factor is
disappeared
you have
somehow.
your
Written back to
Okay.
V. Yeah,
it,
great.
you take
Can you guys hear us?
value, and so your fill factor is what you have here.
Hello?
Everything that's underneath that.
Also, this
That
is a
measured
P. This is what they use in the denominator.
Yeah. So this is what you would get.
The
for
area.
fill-
Uh-huh.
Yeah.
The area after the curve.
Area of,
Nice.
of this square to this circle.
Okay.
Yeah, because that would be like the measured curve that you get, and fill factor is just how efficient it is.
Okay. And again, so the paper which you refer to, actually they refer to, right? So it's of course
Yeah.
experimental paper. This is where they use similar system, or what they use, or it's a different material.
It's a Gretzel paper, like a paper by Gretzel, and I think it's experimental.
Hi. In the classroom technology, we had a mix-up with the scheduling. So they were supposed to be over here the whole class, so we actually got these people that were connected over here, or over here. So all the remote people should be signing into this class now.
Okay.
So we were having an issue.
Okay.
And so there are all the other people that were connecting online,
Uh-huh.
they should be now connected to this room.
Right
Okay.
now.
Yeah.
Okay,
so
we
right
don't need to move to another.
Nope, you're good now.
Okay. Okay.
Okay.
Can you guys hear us?
I'll do.
No.
Let's keep
Should
talking.
tell them all.
You will try to work on it.
Yeah, we'll just check by email.
So detail.
Send
Discard
email
the
to
connection
everyone.
and then
Yeah.
connect it.
Let's not
Sorry
stop.
for interrupting. Can you guys hear us? This is NUCYT.
Yeah. Well,
I don't think they can hear us.
the Gretzel paper, it kind of defined
Hey.
fill factor
Well, I'll send my guy back here.
X over this JV, and so that's probably where I got
Just let
stuck.
your bed know that we're here.
Oh, I did too. On Slack? Yeah, I don't think he's a big slacker.
The intensity of indicant light. And
He's not
again,
on
this
there.
kind of ignores.
Oh, now he is. I think his iPad must go on, like have it on and off.
Here
I like it. I really like Slack.
the estimating formulas for J and V, where again
What?
J that we're looking at is LHE, or the light harvesting efficiency at a particular wavelength lambda, which is defined, which they estimate as 1/10 to the power of -f, which is the oscillator strength at that particular wavelength. And then V, they mainly look at these parentheses, which this is the band gap of the DOS.
And when you say they, it means it's still in a Gressel paper or it's in this current paper?
It's in this current paper. They attribute this formula to the Gretzel paper, but
Okay, but this is their vision on how this can be calculated.
yeah. So let's
What's the
look at.
definition of photoelectric conversion?
So
You know,
first, they focus on
I might know if I was listening to the entire thing, but
here's
I've got like 5 seconds out of it.
uh,
I would
structure
assume it's the amount of energy
for
converted
three different sizes. The
per
17,
energy radiating the surface of
65.
the solar cell.
Converted.
because they kind of
So you have like
ignore
the spectral density, and then you can overlap that with your absorption,
yeah.
right?
So,
So like quantum dots
then they also
have
did Lumo.
very broad, like once they have the onset, it just goes up, right?
Okay, yeah, but so is it defined as like
And again, blue color corresponds to the porphyry.
Blue is
Let me look at something.
does it somehow subtract like thermal dissipation?
Everything which
Yes,
is
and for my
above zero,
max,
your conduction band, your unoccupied state, everything what is below
Oh.
zero, right?
you're talking about
he's
this.
putting it on.
Yeah, but
thing on
then
it.
blue color on these lines
a
corresponds.
porphyrin. He sent the
Color
PowerPoint.
in DOS refers to the TT or the dye.
Ah, okay.
So I guess that is a bit confusing that they use the same colors for these.
Oh, I see. So the colors on the figures and colors on the images not really related. Okay.
Yeah. Okay. So
So
here they
I think it's
notice
this.
each quantum dot size changes the band gap alignment
Sort of
or
square thing.
who has
Like it's the entire thing.
which has the luma. So this first one they refer to as type 1
That's why Svetlana said, "Don't talk about this. Put it in supplementals if anyone asks."
and luma being
I mean, I
on.
can't bring anything from that, so I don't know what any of this really means.
It means
So as it increases,
so the quantum yield of absorption
get to
But
98.
can you kind of just look
So,
on this figure
the green
and just kind of confirm? I think
boxes.
Yield of absorption.
I see.
Yeah.
Your
So like how
upwards-
many quanta can be
so much really
created by a photon?
affected,
at a
especially
certain
C and D.
Okay.
I think they're a little bit more affected in D
Then-
versus, right? But C and D
Uh,
looks much different,
Gamma
right?
D
For the states
is
which
the
are below
solar
zero,
spectra,
for the occupied states, for the valence.
right? So
But
if
your
the quantum
unoccupied
yield
states, the conduction band, right?
here is zero,
It
it
looks
will
like
kill
your blue
everything
is
until
just
you
like your red
get
is
some
moving
Sure.
towards
way
zero.
to get it.
And that's why your blue
So
are covered
then when you
by
multiply
this red,
these two together through whatever,
which is,
you
can
can
be
get
explained by the
a
environmental
line
fact.
similar to this
It's a
where you
small
have
exercise.
your efficiency
So,
as
I
a
mean,
function
the
of
larger
band
the size
gap
of the quantum,
for
the
this
smaller the
case.
band gap, the
So
quantum
then
dots.
there's like
It's different.
optimal band gap that you can
Lines.
get.
So
But am I
Because
right? Because again, I can't really see
like
all the
here,
details.
if your band gap's here, it doesn't really matter much. Because there's not much
So the effect
light
on the
that has that
conduction band,
frequency.
unoccupied states,
So then
is
as you
definitely
increase,
pronounced, more
you
clear,
still
Yeah,
get a
it's
ton of.
rather than on the
pronounced.
valence
Okay,
band.
yeah, I understand that, but in the math, what is it all taking into account? It's more what I'm curious about.
So it takes in absorption and thermal loss.
this,
How
you know, if
That
if
is
you
this J
look-
R. So this is the quantum yield of absorption, and then it's multiplied by the solar spectra. So then you can get like an average or the sum of every photon come in, how many quanta can be made, and then you integrate that over this thing, and then the thermal loss is this more
They also
complicated
said
equation
that this
where it has the quantum yield of creating a
different
like a electron hole pair. It's related to like the energy, and then this exponential here is like your
So,
characteristic loss.
yes, you have
So
to
the more you lose, the smaller, the greater this gets because this becomes smaller and smaller.
the second
The
thing that they did
denominator.
The
So then when you,
So it's a
substitution.
big approximation, not assuming to any specific system.
This
On the
is-
die.
yeah, for this one is,
substitutions on the die.
it's more general. But if you have all these numbers, I think you can plug it into the same formula
Actually,
and get
see that this is the
four
NO2.
specific.
I figured you'd have to take into like your phone on coupling.
That's kind of
It'd be a big thing.
so. Oh, here's the CH3 and
Yeah.
NH2
But yeah, maybe that's just
COH,
a rough
It-
approximation.
and
I think it would
these are
depend
for
on,
the smallest one, the 17.
Yeah.
17 quantum die, and they noted that it causes a charge separation, and specifically, the band gap changes to a type 2 with the
Could you remind again, type 2, what does it mean? Type 1 when your luma is on a die, and type 2 is luma is on a quantum dot.
type 1. My understanding, because there appeared to only be two types, is
By the way, Josh's
when
runs got in
the
first,
HOMA and
rather
LUMA
than my
are on the
40
same
node one
part of
that
the
replaced
model,
the other 40 node.
and then
So when my
type
40
2
node
is
ones
when
got
it's on
killed,
two different parts.
And
So it doesn't
my other
matter
40
which
ones
one
are
is
still
which
just
one.
still.
so now do S
Either it's the
plus.
same or different, okay?
I mean S
So-
plus.
Yeah, I did.
This
And now
it
there's
caused,
free nodes.
Much more free nodes.
So hopefully,
caused a charge separation,
code
it
doesn't
caused
gobble up those free
a
nodes.
change in.
Ben's not
What
running
is the
anything.
size they
Oh,
show
I'm sure
here
he
for
is.
this
He
calculation?
isn't?
How big the dot is?
This is
do-
size
smallest?
17.
what's
Yes,
that
this is the
name?
smallest. So.
No, I know what it is. He's not here.
But do top minus
Particularly
U and then
with
it's
the
username.
smallest, the weak
Top? He's running on the head
donating
node?
and withdrawing groups
Just-
weren't enough
just do
to
it.
cause a charge separation, but the strong ones were, and these are just close-ups of this particular.
So, oh, he's not on. Okay,
And
never
repeat
mind.
again, it
So,
doesn't matter whether it's electron
there
withdrawing or
is-
electron donating. But if they are strong, they both kind of push this unoccupied
guess,
levels
yeah.
of the die to
So
the
for
gap.
him,
Well-
he does a lot of.
Or it's only
It's
when
two
it's
different
donating.
effects. It's two different effects. So the
So he does
donating,
math,
it
computation,
causes the
right?
LUMO die
And due to that, he needs
increase.
to like
So
submit jobs
compare this
all the time
to-
when his jobs finish. So there are cron jobs that he does that
Which one
checks
is-
to see if he
Which
is
one is
running
which one? Which
anything
one
and if
is
he
strong?
isn't,
Like
then
this is
submit.
donating. Your B and
So
A
there's a
and
lot
B
of
are
cases where
donating groups.
He's not
This is donating.
working, but
And which
he'll
one is
just
stronger?
submit
The top is weaker.
as many jobs as will fit in the queue,
I guess
and then
So then your blue is shifting
use
kind
it
of
for 16
towards
hours or
inside the
however
valence
long it
band of
is.
the quantum dot. If
And
you
then do that
increase the
constantly.
strength of the
So he's written
electron
some pretty
donating.
nice scripts.
Yes?
Yeah, I'm using them now.
well,
Well,
yes,
at least-
they
Okay.
didn't state that,
But this
yes,
is what
that is
you
true.
can see with your figures, right?
So yes, so they noted two different effects. The LUMO for the die increases in energy with the donating groups, and so the HOMO is going to be on the die. And meanwhile, with the withdrawing groups, there's a lower die HOMO, which means that the HOMO is going to be on the quantum dot, and so you can exchange which ones the electron moves to based on whether it's a donating or withdrawing group. And another thing that they mentioned is that for larger size quantum dots, it didn't matter if it was strong or weak, both of them yielded a charge separation. So the third thing that they
No,
looked
no, no. What do you mean charge separation?
um,
I agree for the B case and for the D case, but you don't have charge separation for A and
well, they noted that as well, that for the smallest quantum dot size, there was no charge separation for the weak groups. However, for larger quantum dot sizes, it doesn't matter if it's strong or weak.
because for larger size we have these red lines moving and decreasing the gap. That's why your luma will be always kind of inside the valence band.
So, and then the third thing that they did was the zinc. There's two different linkages that they talked about. The first one was having the zinc inside of the TTP like this with a mide linkage, and then the second one, I didn't really fully understand this, but my understanding, basically what happens is that this group right here is that this part becomes separated and this attaches to the zinc, so it creates this sort of structure right here. And they noted that.
So your A, B, in all cases you have zinc inside, right?
Yes, the zinc.
But you have a different attachment of this linkage group.
Yes.
Oh, okay.
So, and they said that the second configuration is
Solana wants me to do
preferable
something
to
just
the
like that with
module
carbon nanotubes.
because, if I remember correctly,
Solana wants me to do something just like that with carbon nanotubes.
Yeah, and I'm doing it
zinc
for
and the
ML,
second one
which
are shorter.
means I'm not gonna do any ML, I'm just gonna,
It prefers the second
Um,
one.
What does she
which
want
is
you to
why
do
they
with
did
it?
calculations
she wants
on
me
the
to do
second
ML.
one.
For this
And
exact
they
thing? Or?
noted
Right.
that zinc caused
General
a charge
charge for
separation
ML,
in
it can't be
all
true.
sizes of quantum.
No, I mean she wants me to run simulations of carbon nanotubes
This
with
Oh.
an arrow
Lumo
hooked to a porphyry,
and on
just like that, except not a quantum dot, except
Well,
in the
if you
changes
look
in
on
ask.
your blue-colored images, right? I guess this is stage
Oh,
volume.
with AM1?
Again, I might be wrong, but it looks like in this, like if in the case of the HOMA, they completely stay just on a die, on
I know.
Not,
porphyry.
It's the same that
But
I've always been
for your
doing.
Luma, it looks like it's a hybridized state, right?
huh?
I'm using full
Or it
DFT.
just kind of,
Oh,
She wants me to just
No?
add to my stuff.
because there's a little bit bluish on
Because I
the
guess
die as
some
well.
other guy's
how,
doing it.
aren't you gonna like totally change your research hard?
I think that's just
Like, are there
the,
bubbles on the die or not?
no, that looks like the nitrogen.
Well, she wasn't too serious, like, you have to get this done for me next week. It's just more like,
So it's really
this
just.
is an idea I have with one of my collaborators.
Oh,
You should think about it.
yeah. So
I'm thinking about
this,
it.
Yeah, I guess
So,
my brain
the
has
fourth
went
thing that
from,
they looked
I
at
used to take,
was
oh, I can do everything to, I need to
Um,
graduate.
this efficient electron transfer.
Oh, she's gonna hate, so,
And, well, so they looked
there is-
specifically at this.
what am I-
Actually, this is one of the problems I had with the paper. I felt like it wasn't as straightforward as it could have been. And because,
Are we back to this? Are we back to this line now?
so they
I haven't been paying
did the
attention.
TDDFT for this, and they got the energies and the oscillator strengths, and so that would give you the current in the J that we talked about a bit earlier, and they also did this, and so yeah, I guess this
Return back.
yeah, I figured.
So what's the conclusion here?
What's
So they
the
have done this and what? So like they show they kind of decompose your excited state, right, into this contribution from the ground state. And it looks like
So they define the current based on the oscillation of oscillators.
yeah, and you well, but you have the V term as well where you really need to kind of overlap your HOMA and LUMA, at least get. Can you turn back to the formula? Yeah, this one, right? So they have energy of HOMA and LUMA.
So
Scale.
this,
For
this
whatever reasons they use 0.3, I don't know, but okay, some
Yeah, that
kind of
was-
scaling.
I looked in another paper and they also had this.
If there's 34 idle nodes,
minus
and I have
point.
2 8-node
Probably
jobs,
just a
why aren't they running?
parameterized part. But if you return back to your so
Now-
what exactly is they took for this HOMA and LUMA?
Try
Um,
S control,
I believe
show,
They
job,
took
Are they
and then
providing any
to,
kind of values for this V term?
like a
somewhere?
single node process, like a single node job.
term?
No,
I
yeah,
missed you.
your formula
Is
is
control
V,
show.
Space show, space control, and the
So
job ID of a like a single
I
processor
think that
job.
yeah,
this
for
V-
you, for the J,
Single
you need
processor
just
job?
this
That's single
latest
node
trans for
job.
this transition
Single node job.
like in
Yeah,
into this
so
one. But for your V,
oh,
it
like
requires
John.
huh?
They are saying that
So-
in the parentheses that's just homologue.
Right, but
And then
but
just
they
do
do have that
SQ.
Yeah.
they can just get
So
the values
do
and
like look
compare
at
the values.
some of
Did
the
they?
like
Are they
do
reporting
do
these
S
values or not?
so S control
I
show
think that they
job.
just kind of looked at the
Show
projected
job,
dots
one word.
No,
rather than
Job.
and
taking
then
specific
get the
numbers.
ID of
Maybe
someone
they did,
that
but they
is
didn't
a
like give a table
single.
or any
Okay.
actual
Well,
values.
looks like okay, so they're not really using this formula for any
So,
kind of
like
calculation
here,
so far.
It would
Yeah,
say
they're not
how much
using
time
calculations,
is
they're
elapsed.
mainly using it
So
to
how-
show that V depends on the
So this is 3 hours, right?
Mhm.
So.
But
it-
then what exactly do
they
you do with
say-
this information on the
No, I mean,
excited
there's
state?
no
Any
sitting
conclusions
open right
on
now
the
that I-
excited state? So what it actually is to that?
Slurm maybe
They
having
kind of
it
decompose,
scheduled
right, and they say
after
that it looks like you
jobs
have this
that
transition
will
from
allow
luma minus
the
1 to
resources to
luma,
be open.
which is about
So it's
Right.
saying after his
minus
job's
10%
finished,
or how
my,
much?
another one of my 40 node job.
So
might
they
be
say
possible.
that this is a charge
Right.
transfer character
Because
because again
if-
it's going from
if
die to
you
quantum
have
dot or from quantum dot to
A
die.
very long process
O minus
job,
1 to
right?
luma
And it gets
plus
submitted.
10, and it's
Now,
15%
that entire time,
of the
Slurm will assume
And the
will
other
be full.
percentage is smaller than
So
this
if
15,
you
right? So
submit
it's
an
a
8
denominated
hour
character.
job,
Because I
no
don't see really
job,
what exactly the
H,
percentage.
it's H to 22 is
and
largest.
there's
And this is
going
just
to
5 to 5
be
character.
40
so-
nodes
For the
for
die.
your job.
So
that was
it
submitted
looks like
before
you
it.
have a mixture of this
It's
pi to
shorter.
pi character
You
really
shove that
addressing
in.
to the die
Takes
and a little
an
bit
hour
contribution of the
to-
charge transfer.
of idleness
So,
to
yeah.
fill a longer time.
For the
assuming
this
that
is a
there will
low
be
state, right?
job
And then
later
the
that will
second
allow
one
the
is the same molecule, just the
eight
second state, or what is your
Oh.
second?
for a week.
Oh, this is
So
where
that makes
34 comes in.
Yeah.
Because
Ah.
this is the 17 and this
So now they finally changed the size, okay.
So I guess they made it
So like,
something like
if
when you increase the
everyone's
size,
running
the
a single
observational strength is
node job,
increasing,
Mm-hmm.
it
but
doesn't need to
bandgap is
think.
decreasing. So
But if
V
it
is
has
decreasing,
40
J is
nodes
increasing, so
to
they
fit,
need to.
But
It
it's
can't
not
just
only
say,
this, it's
run
clearly
everything
showing
once I
that
have
transitions now
hours
becoming
before.
really in the kind of charge transfer
Which is
character.
really
Like you
intelligent,
have this
otherwise
donor
your job that
acceptor
has 40 nodes
splitting, right, with this larger
might not
size.
ever run. If it's saying fill, oh, we don't have fill, fill,
The
fill,
author's
fill, fill, fill.
conclusions were that
Oh, we
the
already
current
have
of this
conclusions.
J
Oh, shit.
increases with the quantum
What?
dot size as HLE, and they just kind of randomly decide to make this sigma relevant, both increase the size, and then the V, or the voltage, decreases with the quantum dot size as the band cap decreases with the increased size. And so the PCE will be maximized with mid-sized quantum dots due to these competing trends, and here's a direct quote. Finally, in a qualitative sense, we can conclude that nanocomposites with moderate-sized CDTE quantum dots have moderate values of J and V, will produce maximum PCE for ZNTTP, cadmium, tellurium, quantum dot nanocomposites compared to the very small and very large ones, and these are therefore promising candidates for the application of dye-sensitized solar cells. And that overall is their conclusion. Reading this paper, I had one major, I guess, gripe with it, and that's I felt like it could have been presented a lot better. I mean, it is a qualitative paper, so there's not that much data to show, but they kind of skipped around and they didn't really, I felt like they didn't really organize like the results section, and hence that's why
So,
we get
I guess,
me not being 100% sure why they did this.
but now it's a little bit better after our discussion, right? We kind of got it, okay. But am I right, or those people who really read the paper or at least look on it, so Ben was doing better jobs than authors for organizing the results?
I haven't read it.
Well, yeah.
Huh? Oh, okay. Okay, good. So, questions?
It's not a question, I just want to know your opinion on your first conclusions. Are you agree on that J will be increased solely by changing the LHE, or
Well, so
What does LHE stand for?
the light harvesting efficiency.
Oh, that's right.
So
And they just estimated as 1 to the minus 10 in the power of the selected strength of this transition at this frequency.
but they have other two factors, that's more
Yeah,
important.
they have-
Yeah.
they have two factors. They kind of threw this in at the end. I didn't completely understand it. And then this final term, I think they mentioned once and never mentioned it again. I think. So overall, they mainly focus on this LHE, which relies on the oscillators. The oscillator strength, which is why they did the TDDFT in the first place. So,
So if that two terms is very small, the LHE doesn't make any difference, right? We shouldn't make any difference.
If what is more?
The phi
Oh,
injection
yeah,
and eta collective is a whole injection, electron injection and whole collective.
yeah, if these parameters will be kind of the dominating, contributing, like the smallest or the largest, right? So then your set parameter might be not as important anymore. Yeah, they definitely can calculate it, so I guess they just leave it as it is and doing whatever they can do. Okay. But again, so it's important, it's just a note to everyone, and I think Ben was really doing a very great job with it, especially at the end. So when you read papers, it's not only that, oh, like, how is it related to the projects which you do and really kind of use it for your literature review, right? Some papers really can be not as good, and it's also kind of a message to you what you should do and what you shouldn't do, right? So, like, obviously this paper is missing this kind of, clear connection between the great formulas which they show and really the calculated results, which were obtained exactly from their models, right? And when they go to the conclusions, that's why conclusions looks a little bit just done very speculatively, right? So they were lucky that reviewers probably were busy not really reading their paper, they just look on the maybe figures, decided that figures are good enough, and they kind of were not very critical with this one. But technically you already see, like, if you want to use, like, obviously we cannot learn a lot of information from this paper because of this missing kind of, connection and explanation from qualitative understanding to the quantitative, what exactly they show in theoretical formulas and in the way how they calculated, right? So, which will just reduce the number of citations of this paper. Like, if they were doing a little bit better job, of course, people will be kind of get this important information and probably cite them much more. Right now, it's just more like, okay, someone was doing these calculations and got some kind of reasonable results. Good? Any other questions? No? Oh, yes? There was a question?
Since did you say, like, I guess with the quantum dot, it reached up to a point where it reverts back to type 1, so wouldn't that also mean there's also like maximas with that quantum dot size?
Well,
or how does that work when it reverts back to type 1, I guess?
I guess I could have looked on the paper that they referenced, which was one of their own papers, but they said that, oh, we did some other research in this other paper and we found that we increased the quantum dot size as...
So it's also with the dye, with the same porphyrin? Or you didn't really look at this paper?
I didn't look on it much, but based off the titles, because I did look at the titles, it's not the same kinds of dye, and maybe it's the same kind of quantum dot, but it's certainly not the same kind of dye. And so they kind of got that from a generalization of previous results.
But again, if we speculate, so the confinement effect will be decreasing the band gap, right? For the larger size quantum dots, for sure. And the gap of the dies, of course, should not be really affected. So let's assume that you have, this is your gap of the die, this is the gap of the quantum dot, which is, well, you start with this one, right? And initially, it looks like you are something like this, right? And this is your type 2. So then when you increase in the size, so suppose your HOMO is not shifting, but your LUMA is shifting due to the decrease in the quantum dot, and then this is your type 2 because your HOMO now is in the quantum dot instead of the die. So the only way to return it back to the type 2,
Type 1.
no, type 2, they said like they go from type 1 to type 2, or whatever, back to have the same kind of, right? It either when your HOMO is also starts decreasing, right? Like right now we see it's only LUMA is changing, but HOMO is not so much affected. In a bigger sizes, maybe your HOMO rather than LUMA is starting moving, and then you have both quantum dots, orbitals, HOMO and LUMA becoming on a quantum dot. Or another thing which you can imagine that maybe somehow the die is also moving, which maybe kind of something like this. So I don't know, but yeah, it's a little bit strange.
Yeah.
So definitely it looks like then if we can assume that this is the right trend, especially again, since they're using different molecule, this kind of statement is probably too strong. So the only way to imagine how it can happen, it's either you really now see the change in a HOMO in addition to the LUMA. So far it was mainly LUMA, but maybe at some sizes of the quantum dot, HOMO starts decreasing, strongly decreasing, and kind of pushing to the red. Or it's just alignment of your LUMA orbitals with respect to a HOMO-LUMA gap. Kind of, they're not fixed, they're also moving when you change in the size, which is also possible to imagine because when you increase in the size of the quantum dot, the surface momentum is also changing. And actually you probably decrease in the static dipole moment of the surface, especially if you go to really large sizes. And dipole-dipole interaction between the die and the surface, this is really what affects this alignment between the quantum dot and the die, and that's why kind of bigger versus smaller might really kind of behave not consistently, but switching the trend or something like this. So I would say again, very speculative, no evidences, especially if they're not working with the same molecule in this other paper. But very good question. Done? No questions anymore? So let's end back. Are we getting back our people from London or not?
They can see and hear us, at least it is what they send by email to Jabat. But we cannot see or hear them.
So,
Jabat, please do not disturb John because it looks like his turn to present.
So this morning I had something through, but yeah, certain jobs weren't going through. Okay, so since I am now working on running both of these types of methodologies, I'm going to do my best to explain how I think about Redfield methodology versus surface hopping. And so this is more of a discussion and a learning experience.
And say, I feel good.
Yep, so this is a learning experience for me. And being cut off from the last portion of Javed's talk online the other day, I was hoping to hear the whole thing, but our connection shuts off at 6:15. Okay. So going through kind of our technical portions of what we talked about on Tuesday, we've had a pretty good idea that we are now interested in how nuclear motion is going to affect electronic population and how those types of electronic relaxations play into things such as photovoltaics or optoelectronics. And we've also heard that there are two different methods that we use in this group, one being Redfield and one being surface hopping. And so primarily, I've done Redfield theory, and so that's where I'm more comfortable. But we'll start with surface hopping. because I'm guessing the discussion there will be longer than Redfield, which is okay. So what we started with, we're interested in molecular dynamics because it's going to give us an idea of how nuclear positions are interacting with one another in a given environment, and how those atoms are changing will also affect how the electronic structure changes. And so this is a very good basis to understand the environment.
And by the way, Daniel, do you see the formula?
Yeah.
Like, does it remind you something?
Yeah.
Yep.
At least by naming, right? But this is probably the formula which kind of, working formula for those papers which you presented last week or when you presented.
Yeah, that's the first thing I noticed.
Yep. So this is a shorthand notation for adiabatic coupling, and a lot of times you might even see it. So this DDR inside of integral and this DRDT. Sometimes you'll just see it d over dt in terms of doing it that way. But because we're interested in the nuclear coordinates r, and I being whatever I am interested in at some time t, that's where we're interested in how these electronic portions of the system change in terms of or where the coordinates are, but we're also taking into account how the coordinates change in time.
John, some people call this non-adiabatic coupling momentum coupling. Where is the momentum in your equation?
Momentum coupling,
Mm-hmm.
in terms of like going from mass to momentum, kind of, the discussion we had in deriving.
In sense of if nuclei do not have zero momentum, then the coupling will be zero.
Okay.
If they, how can you see it in this equation?
But what is your dr over dt?
So dr over dt, okay, so change in position over change in time. So you're talking
Position
about
of what?
change of ions. So in terms of velocity of the nuclear position. So, okay, so if you don't have any velocity, your momentum would be zero. So we need to have,
Which means your dr dt will be also.
has to be a non-zero value. So we're having this non-zero value of the velocity from the dynamics, and that's how it's going to affect the electronic portion.
I would like to address to this formula. So if you look carefully on this equation, right? So again, dr over dt is just the velocity of nuclei, right? And again, if we assume that nuclei move, then the bigger the velocity, the larger the velocity, the stronger the effect should be, right? This is kind of reasonable. So you can think that your coupling, of course, should depend on the velocity of nuclei, right? So which is straightforward from this formula. But on the other hand, if nuclei are coupled to electrons' degrees of freedom, which is this wave function psi, they define the motion of electrons, then of course change, like any velocity or change in a coordinate of atoms, of nuclei, should affect the electronic wave functions. And this is what we have kind of qualitatively, you can understand that this is how it's connected to this middle part with the brackets, with the cat and dog notations, right, for the electronic degrees of freedom. So technically, if someone will ask you on exam, what is a non-adiabatic coupling, right? Or like you can show the formula, but people say, so what does it mean? You can say, well, it's a kind of, it's showing you the strengths of interaction between nuclear motion and electronic motion or electronic degrees of freedom through that kind of, which is of course intuitively clearly should be affected by two factors: velocity of nuclei, the bigger, right, the more, and how much electrons are changed due to this change in a nuclear position. That's it. So very simple explanation what this non-adiabatic coupling is based on this formula. Make sense? Hope it makes a little bit more sense than rather just kind of steering on a formula with and just saying phi is the electronic wave function, r is a nuclear coordinate, right? So if you really try to connect these terms, they really have a physical meaning, and you can really kind of imagine what exactly this means.
And so, with both of these methods, you can go through, run your dynamics, calculate these non-adiabatic couplings, and then from there you can take these couplings and treat them in two different ways. One being Redfield, one being surface hopping. And so the main goal, like I said, is to look at rates of electronic transitions in terms of these types of applications. And so something that, if you want to think about it, so we've seen some of these images where you've got these squiggly lines from the molecular dynamics. Each horizontal line is the energy of one Coulomb orbital. So you can see that as the positions move in time, the energies also fluctuate. And so that's why, if we just look at one vertical slice and then compare it to another one, that's where that coupling comes from. Okay, so I guess I can do that later. So surface hopping. So the way I think about surface hopping, and this comes from the paper by Tolley, which was...
Before you even go there, so again, you got the couplings somehow, right? So then the next question, why do you need to do anything else? Why you cannot just open an adiabatic couplings? Actually, it's a question to the group rather than to John. Why we need to do surface hopping or Redfield theory? Why coupling is not enough? Coupling tells you how strong the electrons connected to the nucleus. Why this is not enough?
We need to look on the electron, how electron is propagating through time. I mean,
So we have
but you have these couplings.
electronic population also influencing the direction of the dynamics.
Okay. And?
Well, and I mean, depending on where it's excited, it can take different pathways.
and also dynamics, coupling is giving us information of the two times,
Each of these couplings.
Each of them.
But you will
yeah.
have a whole matrices of these couplings at different moments of time, right? Because they change in this time as well. Together with your psi changes with time, your phi, psi, whatever you call this Greek letter, right? Your electronic wave function changes with time, and of course means at each moment of time you are getting new couplings. So there is time dependency in these couplings.
You need states to go to? Are you defined states?
Yeah. But what does it mean we need states to go to?
Like electronic.
This index is I and j, this is your states, where it goes from to.
Right.
But you need a direction, right? Because couplings go from I to j is exactly the same as j to I, right? So overall, your couplings is kind of, if you think about coupling should be proportional to the probability of going from one state to another, but couplings just give you the information that, well, you don't know where it goes, from I to j, from j to I, right? And yeah, you will have how they are different, some they might decrease or increase with time, right? But you really need to actual kind of dynamics to get this probability and kind of also include the information on kind of direction, which probably you just expect that the electrons should move from high energy to low energy, not backward, right?
So the keywords here are detailed balance, if you like statistical mechanics, and irreversibility, if you like simplest language.
Irreversibility is the simplest language, of course. Yeah. Okay. So that's why getting couplings is really half of the story. Because again, it doesn't give you it gives you the dependence on time, but it doesn't give you the information where exactly electrons move to, right? So it doesn't really give you real dynamics. Means the dynamics means not only change with time, but also the direction of this initial excitation, how is it really kind of increasing, decreasing, and so on, right?
And so
for this, you need to get some additional steps, some additional methodology kind of to include, which will, as Dmitry already mentioned, either based on the information on the detailed balance, or again, so that you really push your system down in energy, or the irreversibility, which, as we know, much simpler, of course.
Okay, so I'm going to jump to this just because we're talking more about how we think about these two different things before diving into specifics. So one of the couple major differences that when I was thinking about this and putting it together, with a Redfield theory, when you have all these couplings, we end up taking an average of the couplings over this type of trajectory, so you get a very general idea over the adiabatic couplings between these different states. But it's different from what surface hopping is, because now you're looking at a very specific time, and if you would have something with one single crossing, if you would have a large average, you would lose it, whereas a surface hopping, you would get that single crossing into that type of thing. And so I'll try to highlight this a little bit more. One of the other benefits, I guess, or differences with the red field, because we take this averaging, if we have a short trajectory and we know it reproduces the coupling seen even over a long trajectory, we can just use a very short trajectory, so it saves time and materials. Let's see, but with the surface hopping, you can get some of these more, these faster isolated transitions from different states that might be missed with the coupling. So in reading the paper by Tully from 1990, so this was kind of where he introduced like the fewest switches surface hopping. So surface hopping is its own category that's been around for a longer time period, but the fewest switches is an algorithm to make sure that you're not just bouncing back and forth like crazy, but taking a little bit of a broader look around crossing points to determine whether or not a hop is probable. So in the steps that he defined of what you need for surface hopping, so having the system that describes the physical environment, and we've talked a little bit about initial coordinates and momenta. So having this type of molecular dynamics and an idea of what the electron density looks like around those atoms is kind of the first step to be able to go and propagate this type of electronic motion. And then with the way they described it, so you're looking at an equation of motion for these atoms on this potential energy surface, and looking at how the nuclei are adjusting in interaction with each other, but also in interaction with the electronic portions, and then integrating these on just small segments of time, and then looking at the switching probabilities or transitions from one state to another, and pulling those from the electron density that you can calculate. But then there's also different parameters for these types of switches that I'll talk about. And then it's kind of a cyclic thing where, if nothing happens, then just go back and feed it back into this equation of motion, how the electronic structure interacts with or drives the nuclear coordinates on a given potential. So hopefully we'll go through this. So if we want to think about
what are you doing?
so if we think about, so I was just going to draw. So
I thought you were going to show the movie.
Oh.
But drawing also is pretty
So
entertaining.
say we have something like this where we have one potential and two potential, and we have something with some type of electron wave function populated on a given state, like on this state here. So what we might have is at each instant of time, we're going to have coupling between these potentials as we go forward, and each of these couplings is going to give us or work into the probability that this wave function might go down and jump down to this lower potential, something like this. But given that you have some type of a segment of time, you could have transitions that go at almost every integral that they look at, or it could be something that's a little bit slowed out, and that
it's also not zero probability to go not to the state 1 but to the state -1. I mean the lowest one, right?
Mm-hmm.
And there are other ones.
Yeah, so I mean so it's not just two states. There's a whole host of states where you could do multiple.
Technically this initial state can go 90% to the state 1.
Yep. And you could,
I don't know, 20% to the, let's say this one is HOMA, or whatever you call it, right? Then to the next one, 20%, 10% to the next one, and maybe
so
1%, or how many to normalize them.
Yeah, so you could have, an infinite number of
and
bifurcations.
some portion might
of
stay as well on a previous state.
Yep.
In the ideal precise quantum treatment or in surface coping?
In surface coping.
But in surface coping, there's statistical average. In one selected trajectory, you cannot have this branching and splitting. In each selected electronic trajectory, you always have only one orbital occupied, but upon statistical average over several trajectories, you can get this branching and splitting of several percent. Yes, it is. We can.
Otherwise, every of them will just contribute the same portion.
No.
You average them later.
You average them later.
You have couplings between state 2 and 1, 2 and 3, 2 and 4, 2 and 5.
Yes.
And actually you can depopulate your state to all of them, not just to the one
Yes,
state.
you can
This is what I
depopulate
say.
to any of them. To any of them. But
At one run.
if the states in one run, if states are adiabatic, then surface hopping it's different from regular quantum mechanics.
But we already have non-adiabatic couplings. Means you already go beyond adiabatic dynamics, right? Because if your couplings are zeros, then your
Yes.
probability is zero as well.
Yes,
To jump.
there is probability to jump to any of the quantum states.
Right.
But the hop happens not to the portion of the wave function, but to the like the charge carrier or excitation jumps from one potential surface to another one. It doesn't split 50-50 between potential energy surfaces. And it is main argument for people who like surface hopping against Ehrenfest. So it's in one electronic trajectory, charge carrier jumps from one potential surface to another potential surface.
But it's meaningless because you need to average over all your ensemble.
Yes, and then in one ensemble, this hop happened earlier, in another later, in another one it was hopped to another potential surface or up hill, and upon average you get this distribution of percentage. So there will be a little bit, well.
So I mean, so then the average distribution that you get after taking all these different ensembles, how close is it to then just the adiabatic coupling probabilities?
It will be close, but the surface hopping procedure does include irreversibility that is not included literally in the non-adiabatic couplings. So the whole reason to include it is to design quickest possible procedure compared to pure quantum propagation, to take into account nuclear transitions due to nuclear motion.
Okay. Second question then. So when we gave our own definitions of coherence the other day. We were just kind of talking about it. So in doing some of the reading, they were talking about when you have these types of split wave functions, so the probabilities, are equivalent on two different states. They were talking in terms of the coherence of these two probabilities knowing about each other versus not. So, I mean, is that kind of the root of their discussion? Because if you have a decoherence time, then they're just their own separate portions of a wave function that are no longer connected, and they can travel on their own trajectories, just as a fraction or whatever.
After you pass this decoherence time, right? I mean, like as soon as you reach this decoherence. So before this decoherence time, you have coherence system, right? It means they move
So
together.
they are interacted. So that, I mean, they're at least aware of each other, where they're at, and then it just kind of
And another thing, how you can think about it, like let's say if you have two-level system, if you have really your system, like exactly as you wrote here, as you draw in here, let's say these two levels are very splitted from all other bands which you have. So technically your surface hopping will be confused because it really will go to the completely 100% coherent situation, populating top and bottom in a 50%, as you expect to be in a quantum mechanics. Means, although your state number 2 is high in energies than state number 1, right? So the surface hopping, if the states are very splitted from the other ones, will be really populating 50 and 50. It will be not really moving it to the state 1. independent how long you wait for your dynamics will be done. So you will have these oscillations. Well, maybe not exactly 50-50. I don't know.
Whatever.
But you will never really see that you will get populations of your state number one at some very long time, right? And this is again well-known problem for the surface hopping, that it's kind of over-coherent. It has some over-coherency effect, right? So that in reality we never have completely 100% coherent situations, but your surface hopping might give you this absolute coherent situation if you have a difference in a splitting between levels, kind of difference in a coherent time versus decoherence time. If there will be, I forgot which one is small, which one is bigger. If the jump happens much slowly comparing to the decoherence time of the system, then it kind of really ignores it and it makes it coherent instead of decoherent.
Okay.
And then you can trust surface hopping, if this is related to your question.
Yeah, no, that's kind of something. Okay. So to get back on track, to summarize, you can start in one level and you can have it jump down to a second level or have it split between a number of levels. And so we're just going to have a propagation at specific points. Whereas when I was talking about, how with a Redfield you have, say strong coupling here, weak coupling here, you would take an average. Whereas now you can find these isolated portions of strong coupling and have transitions much more likely in the short time period compared to the length of them. So maybe this is too much, but so this is kind of another picture of what I was looking to draw. So you have one potential that you can say the electron is populated, it's following this nuclear potential, or these dotted lines will show that it can jump up to a second potential and jump back down. But the goal is to isolate jumps and get rid of the ones that aren't physically possible. So when we look at a total wave function for electronic structure or material, we can look at like these expansion coefficients, which give the probability of population of whatever electronic state it is in terms of this total wave function. And so now we have an idea of which states are most probable to hold the population.
What you call state is just adiabatic state, right?
Mm-hmm.
Your small phi.
Mm-hmm. Yeah. And then when we talk about these adiabatic couplings and how they transition, so now we're interested in how these coefficients change and populate into a second state. So you have density matrix elements, and then this R prime dk is the adiabatic coupling term. So you have some initial coefficient value, losing population and going into a second state. So in terms of what we can do to work on it is put it into, that you just put it into density matrix notation, so it's a little bit easier to work with. Changing it to this AKJ, and they put the electronic populations in terms of this, which should look familiar from what Jabed had put, or had on one of your slides. At least it's something very similar to what you had. So in terms of, the total population on the diagonal is equal to these elements, from an initial state to a final with an adiabatic coupling that's taken in. And then they play into what they call their switching probability. So when we're looking from one state to another, and what is the likelihood of a transition going from one to another, it takes into account this type of interaction of losing the probability, and if your switching probability has a specific value, it'll transfer to one state versus another. And so that's, like I said, this is kind of a learning experience for me. So I don't know, I'm sure there's lots of questions that I probably won't be able to answer. Or, yep.
So in your equations 13 and 14, what are this A, K,
Mm-hmm.
and A, K, whatever, L?
So the AKK are the electronic populations of state K. So they're the diagonal elements of like these expansion coefficients.
Can you think about it like a density matrix? Elements of density matrix?
Yeah,
Diagonal or off diagonal, right?
Yes. Yep. Yeah. Yeah. So when they put it in this density matrix notation, they just change from C to A, and so now you have the diagonal elements of a density matrix.
And equations 13 and 14.
And by the way, your C here, I might be wrong. Your C here is the same as C in your equation 8 or 3.
Yeah.
Sorry.
Yep. In 7 and 8. So the expansion coefficients for the individual adiabatic surfaces. So it's just a way to write these expansion coefficients in a density matrix format.
So, and your equation 13 and 14 can be interpreted that change in occupation, in diagonal element of density matrix, does depend on the values of the off-diagonal elements. Right? Okay. And then it later on it gives connection to decoherence problem.
Yes.
So if
If it's completely coherent, right? So your off the diagonal element should be 0.
Yeah.
But because you kind of really accumulate
Have that
this
too.
this connection between B and A, it results in kind of more and more non-diagonal elements becoming not 0 anymore, right? Right? This is what you mean by decoherence.
But the procedure of surface swapping to some extent poses a goal to make off-diagonal elements as hidden parameter that is not explicitly followed, because the main observation is only occupations, right?
And so when they're looking at these types of switching probabilities, one of the things that they have is, so the switching probabilities, so they generate a random number and compare it to the probability of transition from one state to another. So I think they use some type of zeta. So you generate a random number from 0 to 1, and if that value is less than the switching probability from 1 to 2, you would have a hop from 1 to 2. But if your parameter would be, you know, something like, you know, your value for 1 to 2, but between your probability from 1 to 3, then you'd have a switch from 1 to 3. So, I mean, I guess that's as to why they choose these random values and then correspond, or, you know, compare them to the switching probability between these different states. I mean, that's purely just.
Does it remind you some other approach, which is also well-known approach, either in physics or chemistry or statistics?
Of just like random probabilities.
Looks like Monte Carlo.
Yes.
Oh.
Monte Carlo.
Okay.
Monte Carlo calculations, right? Which again is based on this kind of just statistical approach, in a sense that you have some random number and the thing happens. So that's like again,
Sure.
you can
Yeah.
put whatever physical meaning for this event, right? What would be the probability of happening or not happening based on this comparison with your just random number. So technically, this is just stealing from Monte Carlo approach.
And putting it into.
One day, someone of us can make
Code.
a presentation. No.
I saw the code from Monte
No.
Carlo.
There are codes. Just introduction of what is Monte Carlo and how is it connected to surface hopping.
And yeah, be careful, don't go to quantum Monte Carlo, it's a completely different approach.
Okay. So that was one question I guess I had.
There's alternative name.
Okay.
Throwing a dice.
Okay, so
Casino.
I'll just talk briefly on red field theory. So because this is, I guess, something we kind of talked about already this week. So this is the second way to take our adiabatic couplings and get these rates of electron transfer. So this term Vij is an adiabatic coupling. We had Aaron talk about correlations between these types of adiabatic states. And so taking an autocorrelation function that he talked about, of just between two of the same function, and taking a Fourier transform presents this Redfield tensor. And so the Redfield tensor gives the transition probabilities, going from plus to minus and minus to plus, so building two halves of a matrix and putting them together to provide these values. And so in taking an average of these values, we now have just a single set matrix that describes the entirety of a trajectory and allows us to look at the electron density matrix and propagate it in time. And so this is the Liouville portion of the superoperator, and then this is that Redfield portion. And so the Redfield, like we as we just discussed, is how does the nuclear motion drive electronic change? And so this is the electronic portion, and then this is going to be the nuclear portion. And so having these two operators act on the density matrix allows us to solve for eigenvalues and eigenvectors, which can be used to solve for expansion coefficients and solving the density matrix at some time t.
Can you go one back? Very challenging question. Do not fear if you do not answer. Where is irreversibility? Where is detailed balance?
As we know, it's very simple.
How does one make sure that relaxation goes towards decrease of total energy? Where mechanically it is inserted, or where it is smartly skipped to shorthand notation?
So I want to say it's contained in the Redfield portion.
Maybe one line above.
In here, so so going back to here, but because this is the non-elastic portion of the change in electron density. And so you're talking about the Redfield tensor in terms of going plus to minus and minus to plus on two different halves of this matrix. So I mean the probabilities of transition, it should be a square matrix, or I should say, mirrors of each other from plus to minus, minus to plus. So in terms of only going in one direction versus not, so you take a single portion of this.
So it is area to discuss, not for such short meeting. It's like maybe for 3 meetings to go. But all of these coefficients are to be multiplied by Bose-Einstein distribution. At frequency of transition, which gets larger or smaller depending on whether it is uphill or downhill transition, and depending on where these transitions are going to, whether it is applied to population or non-diagonal elements, this factor will take different values, and therefore transitions uphill and downhill will have different weights.
But what's the units?
Dimensionless.
They're not dimensional.
Bose-Einstein.
Your H is joules times second. This is joules. So you
Bose-Einstein distribution is number of.
So H is not.
It's not H. It's N.
Oh, okay.
Very calligraphic.
And so, so solutions of these expansion coefficients So we look at the density matrix in time 0, and we change initial populations from state A to state B. So we're moving an electron from one state to another, and then recalculating the coefficients to follow where the population is in time.
What is in your first line of equations?
So this is the Liouville operator, the Redfield operator. This is the electron density matrix, and then these are the eigenvalues and eigenvectors of the diagonalization of this.
So how do you call this calligraphic R capital in the codes?
So this is R.
Okay.
So R. That's yeah. So yeah. So this is the RR file that we generate. Okay. And so, because we're interested in a non-equilibrium electronic state, this is in terms of taking population away from state A and putting it into, or state I and putting it into state J. And so we're, just population of A and B at time 0, and then it's just a Dirac function. So this is just a population factor. And like we talked about earlier this week, we're just looking at an energy expectation value of the states dependent on where the population is at. And by looking at this, taking it into a normalized value and fitting it with a single exponential, we can get the rate of relaxation out of it. So
you're answering the question how to get relaxation rate. And a couple of group meetings ago, there was a discussion on this subject.
So if you remember the dotted black line or the solid black line running through the orange or blue on those green figures, this line is that's what's fitted here, this average expectation, and you get the rate pulled out fitting that line, or what would be here.
So why over right integral gives you rate?
Why this gives us rate?
Yes. Can you prove it if needed?
So so it'd be the inverse of this. So you just want to take, because you take a natural log of both sides and then.
Not
Right,
whole,
'cause
you just integrate exponential, right?
Well, yeah, you integrate, get your KT out of this over some integration of E and solve for K.
Yes.
Oh, okay. Okay.
But why you expect that you will have just a single exponential behavior?
Because it is easy.
Well, I'm just wondering, is it rate or rate constant? What is the?
Well, so the values are given in inverse picoseconds.
Yeah, it's because
It's a
you
rate constant, but
assume
people
that
call
it's
it
singular.
Yeah.
Okay.
So it's not relaxation time, but rate constant.
Is it okay?
Yeah. But no, so Aaron has done some work on looking at multiple exponential fits to different populations. Because if you get something where you have a system and it has like a metastable state that isn't quite to the HOMO or LUMO, you can have a long-lived life carrier or a charge carrier. So you have to look at two different rates, and then you can compare electrons versus the first rate versus second rate, and do some.
So what is your infinity T? Is the one at the frontier orbital?
Here?
I mean infinity. I mean.
Yeah, because so the subscript of E can also be swapped out for H. So the electrons and holes are solved in the exact same way, just with different ones. Yeah, because you're only
in infinity. I mean in the
which actual number in
which
computation is used to replace infinity?
Infinity. Yeah.
like in term. Oh, you're in terms.
No, I
of
mean
like
in the middle equations, the energy one.
here.
Mm-hmm.
So this would be what
It's the same infinity in middle equation and
Oh, okay, yeah, it's time.
So looking at how these energies are changing at some time versus the normalization, and this energy value. So what I would say is just like the ground state.
Yes.
It's just gonna be like a steady state.
So It's philosophical, but there is a very strict answer. Last point of trajectory in the simulation.
Okay,
in
so
other-
I mean, as long as the time is gonna run, and that's gonna be the end of it.
Yep.
Okay.
In other words, how long trajectory would be sufficient enough
If
to
if the relaxation is complete, then you make longer and longer trajectory, and your rate stop changing. If your trajectory is too short, then you observe change of the rate as a function of the length of trajectory.
So you always do several trajectories to see whether you are reaching your limit or not?
It should.
Yeah, because that was, and one of the parameters that Aaron had circled on one of his presentations, because it's an exponential time grid, so you can change and play with those factors on how long your trajectory will actually project. And so if it's something that's a really short trajectory, you can go in and modify that, and your rates are going to change a little bit. And I think that's the end of it. But this was going to be my conclusion slide, but beneficial for having a material that's relatively has motions that stay relatively stable, so you can save resources in running shorter trajectory. Surface hopping provides a better definition for systems that have fast or isolated transitions or crossings. So at least 2 points to take away. But I'm still learning, so but I'll take more questions if or discussion if we want to have it.
Okay, good. Thank you, John.
But have you ever checked, since it's really kind of the main issue which is making this difference between two approaches is your average couplings, right?
Mm-hmm.
But again, the question is whether your average is really good or not,
Right.
or good enough.
Right.
It's very easy to check if you look on the standard deviations,
Mhm.
right? And if your standard deviations are very small, you're good. If they are really big, then you probably cannot trust your data. So I don't know, have you ever, have you been ever checking your standard deviations when
Well-
you take this average couplings kind of to convince yourself at least that you are fine with this approach?
So I haven't taken standard deviations of it. A simpler way is when so like these kinds of energy fluctuation figures. So in looking at the amount of fluctuation and if there are very sharp like amplitude changes. So those types of sharp peaks inside the fluctuations can either one correspond to some unique nuclear configuration where the energy just jumps up, or you might have multiple crossings between different states, and because they're projected as adiabatic, you won't see the crossing. But if you have something that's more or less very similar throughout the entire trajectory, you know that the energies aren't necessarily going to have a number of large crossing areas, and it's going to be relatively the same. I mean, it's a very non-scientific way of looking at it, but having a rough idea of, is there a ton of change due to the nuclear motion and energies versus something that's similar. But the standard deviation would be a good way to go.
Yeah, you have your set of non-batic dynamics couplings even for a short period of time, right? You can easily see how much it changes for each state, for each pair of states. And I guess you can just take the nearest one for simplifying the procedure, which is the most dominating probably, right? And kind of check how consistent your
It should
average
work.
is.
The couplings oscillate, but the couplings between different pairs of transitions oscillate with different amplitudes, and probably it's possible to analyze standard deviation. Yeah,
For couplings, not for energies.
for couplings, yes.
Because again, like as you said, like this peaks in the energy might be not as pronounced. Like you see a big peak, but your coupling still might be small. Or
Right. It could just
Not
be
really
everything
affected,
shifting,
right?
just the energy versus the actual spatial overlaps. Yep. But, so hopefully that kind of helped.
Other questions?
Just a second, I guess I got a question maybe from Brad.
Oh,
Okay,
Oh,
thanks.
Braden.
Braden
Yeah.
or Brandon?
No, Braden. I got a notification, but I cannot see the
Great, and please
Okay,
present your question.
he said no. Yeah.
No?
What?
No.
No?
I have no questions.
Oh.
Last
His message was no questions. I see.
last
Okay.
chance to ask a question to. Last chance for today to ask a question.
It's not a question. I want to know your opinion. If I ask you to choose one, which one you think that give you more better agreement with experimental result or empirical?
The one that is accepted for publication.
Well, it is a cynic.
No, it's
And from theoretical point of view, yeah.
right. So, like a lot of our work has always been, rigid semiconductor materials, whether they're nanoscale or two-dimensional bulk, whatever it is. When you have rigidity in your structure and you don't have a ton of nuclear fluctuation, going through red field can save you quite a bit of time because your bands aren't going to be crossing or bending as much. But once you start adding things, so even in perovskites, when you start having, or organic ligands, when you start having materials that are going to fluctuate and move or rotate quite a bit, it plays a larger role in how the electronic energies are going to shift a little bit because now you have drastic orientation changes. So surface hopping, I think, can be very useful in those types of situations. It's just you're going to have to put a lot more time into getting it because depending on how the time scale of the atomic motion you're interested in, that's how long your trajectory is going to have to be. So like those rotations that we're talking about with methyl ammonium, if they're on the scale of 2 to 5 picoseconds, you got to have a really long trajectory versus running it for 100, 150 femtoseconds and potentially having a good enough answer. So.
I guess Levi is typing something.
Ah. So discussion activates.
No, you're just saying Levi is typing, so I don't know if he's typing questions.
Maybe he's typing, I do not have any more questions. Levi, if you hear us, send messages to Jabet in telegraphic style. Hit enter after each word so that Jabet is not bored to watch you typing.
Okay, original question is he's asking if there have any difference excited state versus ground state. Which method should we work in?
Which is exactly the same arrows will be. Because they are based on the non-adiabatic couplings calculated for the ground state, right?
Yeah, so it's not like you have an excited population calculating those dynamic trajectories and then calculating the couplings. It's all.
So your corrections to the excited state should go to the non-adiabatic couplings. And then which method you use will be not really affected. Well, except that again, your excited state might be more flexible and more changing than the ground state. Then again, this is pretty much the same story as he already discussed.
So if you're able to compute non-adiabatic couplings with excited states, then after that you can feed in such information either with surface hopping or into red field approach.
But for sure, it would be much faster with red field approach. And maybe for excited state, this would be the best way to go.
He started typing something.
He took your advice, Dimitri.
Huh?
He took your advice. It's just one word.
He's saying that if that compound is much floppy, I mean, maybe they're not rigid, so they don't work.
What won't work?
This won't work, maybe this comment is not working. And
Which comment is not working?
and you said that.
But John didn't present any specific.
No, I mean, I
compound.
said if this excited ground state is the same, error will produce. But he's saying that if compound is floppy,
Yeah, so
I mean,
not rigid.
I mean, not rigid,
Yeah.
So in that case, it's the same thing.
What is
Well,
the same thing?
I mean,
So if you just had a big organic molecule that you're looking at, and there's a lot of nuclear fluctuation, then I would probably go look at surface hopping. That's a first option.
There is another way that several of people in the audience did practice. If there is a flexibility of bond, if the bond is not rigid, then one can explicitly assign most interesting, most important nuclear degree of freedom into quantum domain, and just consider quantized degrees of freedom associated with this degree of freedom, and just increase basis. And it will. No one wants to do it. It is too expensive, but it is a rigorous way to address flexible ones. Like parameterize it in a sense of Marcos theory and explicitly quantize all levels.
What about the coherence time perspective? Which method would be more applicable?
Which method is more applicable to a coherence?
I mean, if the system is more coherence,
Oh, which
we
one
know
would
the
work
surface
better?
of-
If
yeah.
so, if you have an issue with coherence, which one would be better?
Mhm.
I mean, so like we talked about earlier, the off-diagonal elements are right. We're talking about like decoherence, driven from looking away at different states. I mean, we haven't. I guess we haven't. Well, we've discussed it briefly, but it's not like we have anything written in Redfield to, or I guess explicitly define it, other than like those off-diagonal elements. So I guess I don't know the impact on that versus surface hopping.
Both approaches do have ways to take into account effect of decoherence. In density matrix approach, off-diagonal elements and decoherence are natural things to treat. But there are theorems that if couplings are small and dynamics is long, then effect of decoherence can be to some level neglected. So the dynamics of diagonal and off-diagonal elements decouple. It is a strong approximation, and if one goes backwards beyond this approximation, one needs to explicitly include off-diagonal density matrix elements and portion of the Redfield tensor to propagate them. While in surface hopping, it is also special approach to.
But in a way, how the surface, like in your case, you said like you really just include this term, which is there in a theoretical part, right?
It is in theoretical part, but in many applications
You
we
just ignore it.
Ignore it
Right,
intentionally.
but technically it's there.
Yes.
And you can treat it.
So if
but in surface hopping, we don't have this term, right? It's really nothing to contribute directly from a theory, from a theory point of view. So people correct surface hopping based on just getting a correction in addition. It's not like you have this term and you just neglect, right? And then if you want to make it more accurate, then you kind of return it back. But for surface hopping, you really need to put something extra to resolve this problem. Right?
More questions, one?
Ask his questions.
He's actually means saying that, suppose like in organic compound, we cannot use these methods. But we are talking about, we are doing.
We are not using it for organic
Yeah.
compounds. This is exactly the reason, yes.
Our discussion is comparison between two methods, but he's saying that
Neither of these methods
neither of
can
the
be
work
used for the organic molecules if non-adiabatic couplings are calculated based on the ground state approximation. Yeah.
And the explanation of why Levi is asking these questions, because he is involved in calculation of photo-induced explosions of small organic molecules.
Yeah, these methods will be not working in this case.
More questions, one? More questions, two?
Brandon asking that how do this method changes with given change?
What?
Given change in DFT. Oh, I mean, if you use the restricted or
Will not
unrestricted
depend.
DFT.
Spin restricted.
Would you like?
Spin restricted, unrestricted.
Oh, so that the question spin versus non-spin.
Yeah,
Kind
I
of
guess.
the types. I mean, so the DFT calculations are different in a way that it's spin polarized, spin unpolarized versus non-collinear, and I mean you can treat Well, I mean, with Redfield, we've been able to treat all three of them in a similar fashion, just taking the different segments that come out of DFT and putting them together. With surface hopping, I guess I'm not 100% sure on how they propagate two different spins with any like a split probability. I mean, is it similar? Can you split it in terms of propagate a spin up and a spin down, or are they intertwined with one another?
It should be possible. There is no.
Again, in formulas, you can like if you can split it in your non-adiabatic like
One, you
because
can
your
split it
non-adiabatic
in two
couplings are
separate
you can calculate non-adiabatic coupling separately for spin up, spin down, right?
Yeah.
And again, if you have a mixed, I mean, if you include the couplings,
and just
spin
go
orbit,
that
then
way.
it does matter, right?
So it's a question to implementation, not to the.
The theory by itself is of course not affected, and it can be done very easily. The question is how to modify the overall coding of the things. Of course, coding probably will require extra work for including it. But this has been already done by you, right? So I think Erin also
They'll change your rates a little
have
bit.
been
so they
changing
change your
the overall approach to include the speeds.
Yeah.
Spin up, spin down, and but if you use your spin orbit coupling, then you don't need to change anything, right? You then just run your
Well,
dynamics as it is. Am I right?
For the most part.
Because all your states, you cannot distinct anymore between your states, which one is up or down.
Right, there's,
yeah, it's just spinners.
so I guess you can include magnetization to incorporate like spin flip, or to see when a spin flip happens.
Just to track.
Yeah.
spin flip, not
But it
to-
should do it by itself though, or it should implement it by itself.
Or just for analysis to understand
Yeah.
what's going on. But technically, you don't need really to change the codes if you include
Right.
the spin orbits.
Yeah, just to read just a little bit different formatting.
Good, I think we're done.
Okay.
And we meet next Tuesday, but not next Friday, right? Because of extended holidays. For next Friday.
No, no,
What's going on?
we don't have meeting
July
next Friday.
4th.
Oh, yeah.
That's
that'd be-
exactly what I
yeah, it's
said,
coming up.
did I? So we have July 4th on Wednesday.
Let the force be with you.
Uh-huh.
But so we meet on Tuesday just before the July 4th, but we don't meet on Friday after the July 4th. Right?
Who is not present in the following week?
On
Because
Next
on
Tuesday,
Friday-
coming Tuesday.
Oh, next Tuesday, I don't know who's presenting.
I will be
Oh, London.
doing a research update, and I guess I don't. Who else is going? Is it just me, or
Yes. You.
am I supposed to go for 2 hours?
No, you can go
Okay.
really
You can go
30
for 10
minutes.
minutes, but then we will let you enjoy the questions.
Right. Yeah.
Tuesday, right?
What's that?
Tuesday or Friday?
Tuesday.
Tuesday.
Anybody presenting besides Alyssa on Friday?
No.
Because I meet
Not
John's
next Friday, but
today,
next Friday. Only Lisa is assigned so much so far, but if there are any volunteers, you're of course welcome.